Welcome to Radar System course. Today we will see a circulator as a duplexer. So we have seen earlier that a balance mixer. So in the balance mixer, we have seen that were a transmit receive switch or a magic T junction across the or in front of the a mixer there. So now we consider a circulator here. So circulator it has a three port. One port is connected to the antenna and another port is connected to the your transmitter. This one we say antenna. One port is connected to a transmitter. Sorry, you can say that is about a transmitter here, and we can say that another port that is about a third port. We consider it is a receiver now. Okay, that is a part of a receiver. So in which we use a transmit receive tube. Okay, so that tube is just like to control the whatever the transmitted power not to reach to the receiver there. Okay, TRT. Then we have a controller or a limiter there for your receiver signal. Then the diode limiter it will use, and after that, that section is a receiver. Now, in the case of a circulator, this portion, that circular portion, is nothing but a circulator. You can say that this one is a circulator, and how the circulator work at a time of a transmitting signal propagating toward the antenna. Then antenna transmits the signal in a space. At the time of receiving, signal is propagating to the receiver there, receiver node. Only one-way transmission is takes place from the transmitter to the antenna, then from the antenna to the receiver. So no communication or no signal propagate from the transmitter to the receiver here. That is the role of a circulator. It will propagate the signal only in one direction from transmitter to antenna, no signal at the receiver. From antenna to the receiver, no signal at the transmitter. Okay, that's why we can say that a circulator. A single antenna can be used here for transmitting as well as a receiving purpose. So this circulator, it is about a three port, port 1, port 2, port 3 here. And this three port, we can use one port as a transmitter, one port antenna, one port as a receiver here. And we doesn't require any protection or any component in between the transmitter and receiver because it propagates the signal through the to the antenna directly, no signal or no any leakage to be transmitted to the receiver side block. Okay, so these are isolated ports. If you see that a transmitter and receiver, these are the isolated ports. When we transmit a signal, these are the isolated one. When we are receiving the port, this one is isolated. At the time of transmitting, we just use this particular way your signal will be transmitted at the time of receiving through the antenna from the antenna to the receiver there. So it doesn't require any isolation between a transmitter and receiver. If we have a circulator here, so no need to use any isolation between the a transmitter and a receiver there. But what happened here? Due to some mismatch occurs at the particular port, so then there will be the reflection from the given particular port. So some power whenever we transmitting some signal, transmitting the signal to the antenna. So if any mismatch occur at this antenna here, so due to mismatch, reflection occur from the antenna. So reflection is nothing but that signal is propagating to the a receiver side. Okay, that reflected signal. So that's why here is one TR tube is used. So this TR tube, or we can say that it is about a transmit receive limiter, or it is a, a switch or a gaseous switch. So it will just allow to propagate the signal only in this direction. Okay. So likewise, so that's about a TR tube here. So it it is act as a limiter here. So because providing the limiter, so we can consider that before that this particular switch is to be used here. Okay, so that is about a ATR tube here. Then we can say that there is a limiter. Generally we use a limiter for whatever the discharge from this particular gaseous tube occur. Okay, so this one is about a TR tube is nothing but a radioactive gas tube TR switch here. So that's why we are supposed to use a limiter in combination with a TR tube and a diode here. So that's why we can say that it is about a TR limiter, and that will protect the a receiver here. So TR limiter that will protect the receiver here. So some leakage occur in this particular gas. So that's why it is just like used with a combination of a TR tube as well as a diode limiter. Generally, if you see that in a TR tube, there is a radioactive prime is used. Okay, radioactive. So that's why we consider uh, TR tube, and this tube doesn't require any voltage. Okay, so that's why we consider along with a diode limiter here. So then, why this diode limiter is because some reflections occur from this antenna due to any mismatch. So spike will occur. Okay, and that spike may damage a receiver. So that's why we can consider this limiter here. And again, we can say that if we have any clutter signal will there, so that will limit that particular level of the signal. So that's why we supposed to use a limiter here. Okay, then we say that a receiver other blocks are present in a receiver there, and that is to be used in a duplexer there. So another considerations for the duplexer, so instead of only a circulator, we can use a various kinds of a component. Instead of circulator, we can use the magic T here. Okay, so that magic T again use like a switch. While transmitting, only one particular antenna will be used. While receiving, okay, that ISAN transmitter and receiver both are isolated if we are using a magic T there. That's all about, we can say that a circulator has a duplexer there. But when we are using this particular TR tube as well as a diode limiter, so there are some drawbacks here. Okay, so insertion loss because of inserting those particular components in the a receiver side there. Okay, so there may be the insertion loss occur due to this particular device. Now next we proceed to a match filter. So we have seen earlier that is about is signal is to be received. Okay, so that receiving the signal matched filter receiver. Earlier we have seen that a receiver block. Generally, if you see that a radar receiver, it will detect the whatever the echo signal received at the receiver, or a signal reflected from the target, that is nothing but echo signal that will be detected by the radar. And then whatever the information is received at the radar, and that information, that echo signal, that will provide you the information regarding the range as well as a velocity of a target plus a position, or we can say that azimuth or a elevation angle of the target there. So now, while receiving any signal, okay, so in that case, at a receiver, we are getting the echo signal, and that echo signal is consist of what? It has a signal information, or we can say that a tracking, as well as we can consider that it has a noise here. So at a receiver, we need to find out what will be the a signal to noise ratio at a receiver signal to noise. So to increase the signal to noise ratio, so we need to use some particular frequency response function, or within particular band of frequency response function that signal is to be received. So that will improve the signal to noise ratio. So then we will see that what particular component, what particular network or a filter that will be used as a frequency response function, and that will increases the signal to noise ratio. And that network is called as a match filter there. So generally, if we have a limitations of a echo signal, so it has a information, and your receiver is to be highly sensitive. So it will receive the lowest probable signal, and then we can detect the target, or we can identify the target in any environmental condition. So we can say that we need to separate out a signal from a noise here, so that a signal to noise ratio will be improved. Now, what type of a match filter functions we use here? So generally, a frequency response function we can define in terms of a h of f here, and that function has some amplitude as well as a phase. So we can represent this particular function with respect to a amplitude and a phase. Means we can say that at a receiver this frequency function, we can say that that will represent the amplitude of a receiver signal, that will represent the phase of the a receiver signal, and then what will be the required bandwidth for the receiver. If we consider that a bandwidth is a large, okay, we can say that receiver path bandwidth. So in that case, so that bandwidth is large, so occupation of a signal by the receiver will be large there. When we can say that a large bandwidth occupied signal will be large within a particular band of frequency, and because of that a noise will be introduced in the network. So we can say that if we have a larger bandwidth or a wider bandwidth or excess bandwidth, so then noise will be introduced in a circuit. So we can say that for this we consider a wide bandwidth. So due to wide bandwidth, what happens? We will provide a large band for the signal, okay, occupying the signal within a particular range. So that's why that range increases, a noise will be increasing. Now, if we consider that a narrow bandwidth, so instead of that, we can say that there will be a narrow bandwidth. Okay, so instead of a wide bandwidth here, we supposed to consider that a narrow bandwidth. So now what will happen when we talk about the in a narrow bandwidth? Means we can say that occupied signal level for this wide bandwidth will be large. Okay, so in the case of a narrow bandwidth, what happened? The signal occupied by this narrow band will be small. So in that case, because of a narrow bandwidth, so noise will be decreases. We can reduce the noise. But when we are saying that, when we are reducing the noise, because of a narrow band. At the same time, we can say that a signal occupied by this within the particular band will be a narrower one. Okay, so we can say that while receiving any information from the that echo, okay, echo signal, we are getting the echo signal. So whatever the informations we are getting from this target, if we are not providing that much particular bandwidth, so some part of information of a signal we will lose there. With another case, we can say that we can say here for a wide bandwidth, noise increases, so signal to noise ratio reduce. But for this in narrow band condition, for this particular condition, a signal to noise ratio increases. So for this condition, what we can say that a signal to noise ratio decreases. We can say that a signal to noise ratio decreases. But for in narrow band, we say that a signal to noise ratio increases. But a limitations regarding what? For this particular narrow band, we will lose a part of information of a signal. Okay, so then what will be the required bandwidth for your receiver? So in that case, we supposed to choose instead of a narrow bandwidth. Okay, so we will use a optimum bandwidth one. So solution for it, so we need to choose a optimum bandwidth. Optimum bandwidth, so it will receive, a, it will reduce in noise, it will maximize a signal to noise ratio. Okay, so we need to design a receiver in such a way that that bandwidth of a receiver will be optimum and a signal to noise ratio is to be improved here. Okay, that's about the requirement. So now how to find out what will be the optimum bandwidth required by the receiver there. So that's why we need to design, or we need to find out what will be the frequency response of a system here. So at a receiver, for a optimum bandwidth, the receiver characteristic is to be optimum one. And then for a optimum characteristics of a receiver, we need a frequency response function, and whatever the signal we are receiving, that is a received waveform of a signal, that is to be considered for the optimum character or a optimum bandwidth. Because at a receiver, we say that ultimately from the mixer, okay, so we have a signal received from the transmitter there. Okay, so we can say that, okay, so we can write in another way. We have the antenna. From the antenna, we are getting the signal that this one is a mixer. And for this mixer, we are providing a local oscillator. And after that, this one is a part of a IF. Now this IF block that will provide you what will be the bandwidth of the receiver. Okay, so means to provide a signal from the mixer to the IF. Okay, at the IF, we need to consider here so that a limitation regarding the a bandwidth. So we can choose a signal that bandwidth at a IF stage. So here the bandwidth of a whatever the mixer stage will be a different. Okay, so bandwidth we consider at the IF stage will be different. Okay, so here the bandwidth will be different here at this particular portion. So we need to consider the a bandwidth. So generally we say that your system or a receiver is about a separated right one. So in that case, we need to talk about that what will be the IF bandwidth. So we design a function. Okay, that function, or we can say that a frequency response function h of f and that will maximize a signal to noise ratio at the output of the IF. So here we are getting the higher signal to noise ratio. So at this particular stage, bandwidth will be different. At this particular stage, at IF, we choose a narrow bandwidth. Okay, so that's why we can say that we need a frequency response function, and that will be a portion of the receiver, and that will be in between the antenna terminal to the output of a IF band. Okay, so that is about that will improve the a signal to noise ratio. So we use a IF here, and that IF will be considered as a filter with a gain. So that's why the frequency response function of the filter, okay, that we can consider that is about h of f, and that will define you how to improve the a signal to noise ratio. So for that purpose, we need to find out how to obtain the h of the given particular function. So for that purpose, we need to know about a receiver. So what will be the received signal waveform we have received at the receiver there? So and what will be the frequency response function for this particular h of f? So h of f we can write in terms of what? A this one is about a gain of a filter. Ga is about a gain of a filter, and this s is nothing but a complex conjugate of whatever the signal waveform we have in terms of a frequency. Okay, this one is about a s of f. So s of f is about a signal and a complex conjugate of it. Okay, so that's why s of f, because your received waveform will be of a s of t. That is about your received signal. Okay, so that is about a received signal, and that signal has some particular level amplitude, or we can say that energy. Okay, so in that case, so we need to consider that a signal waveform with respect to the noise. Okay, so frequency response function is to be a linear here as well as a time invariant filter, and that will maximize the a signal to noise ratio. So h of f is equal to gain of a filter. This one is about s of f is nothing but a complex conjugate of your signal, and we have a exponential of minus j twice pi f. That is about a signal. Okay. So generally we say that we have a s of f is nothing but the whatever the input signal there, and that is nothing but what expressed in terms of a Fourier transform. So this s of t is a signal waveform, and we have a exponential of minus j twice pi f t dt. Okay, and this t1 is nothing but what the fixed value of a time. So here where we are getting the a maximum value of a signal to noise ratio. So generally we say that if before IF, okay, whatever the signal echo signal we have received, and that echo signal consists of a noise, and that noise is nothing but we consider it a stationary part. Okay, so for example, we know that a stationary part, or we can say that a stationary noise is nothing but a white noise. Okay, we can say that a stationary noise is a white noise. Okay, so that noise is nothing but a stationary. So we can filter out that particular noise easily because that noise part is about a stationary one. So we use a filter function h of f so that that will be easily remove the a white noise because that a filter function it has a Fourier transform correlation of a signal here. This one is about a signal, a transform correlation. Okay, so this one S of t is about a signal waveform. And so that's why, because of this, okay, so we can say that H of f will be improved. Okay, so we can say that that will use to increase the a signal to noise ratio. So we are using here H of f for the given particular filter, which is a complex conjugator of the spectrum of a received signal. And their waveform is nothing but what? Exponential, means that is about the phase of whatever the a signal there. And then that part we can consider here, this particular portion is a part of your the signal, and this particular part is nothing but to be used for the phase part. So in that case, we can find out what will be the a delay across at the output here. So in that case, we need to know about a frequency spectrum of the received signal. What will be the amplitude of a frequency spectrum of the signal? This one is about, you can define S of f. We can say that in terms of the amplitude here, the magnitude of S of f. And the phase spectrum we can define in terms of what? A minus j phi of f. That is the thing, okay? A phase spectrum. We can say that this one is about a magnitude and this one is about a phase spectrum there. And then we can represent here, or we can write a h of f in terms of what? A phase function as well as the a magnitude function. So how we can write here? So the match filter we can say here. So we can rewrite in terms of a magnitude exponential of minus j y m, that is for the phase spectra of a match filter there. Okay, so we can say that fm is equal to s of f, that is about the magnitude of a signal, exponential of, okay, so we can say that exponential of j, we have pi s of f minus twice pi f t1. Okay, so this one we can express here, and this particular portion we can consider here exponential. Okay, so this one, so we have the ah of f here. So this one is a frequency response function, and we are ignoring here this gain of a IFM. Okay, so that is about, we have considered the gain earlier in that expression. Now we are writing in terms of amplitude, so in that case the gain will be a constant, so that's why we are ignoring this particular one. So that's why we can rewrite this equation h of f with respect to a phase and a amplitude here, or we can say that h of f is nothing but a frequency response function is equal to S of F here. And we can write in terms of phase phi m of F is equal to phi S, whatever the signal we have, plus twice pi F T1. Okay, this we can. So we can say that the amplitude of the spectrum of a match filter we have used here. Okay, amplitude of a match filter spectrum, that will be near about the same with the spectrum of the signal. Okay, H of F is equal to S of F. But in terms of a phase here, phase spectrum of the match filter phi f phi m of F here is nothing but what? A negative of the phase spectrum of the signal, this one phi s of F here, as well as a phase shift proportional to the a frequency there. Okay, so we can say that we have a function by t1. Okay, earlier we have considered that. Okay, so that's about a phase shift exponential function. Okay, twice by f of t1. Okay, so that's why we can say that the match, this one is a magnitude and this one is about a frequency response function there. So we can rewrite in terms of what? A impulse response also. So match filter can be represented in terms of impulse response. In that case, we can say that h of t is equal to minus infinity to plus infinity here, h of f into exponential of j twice pi f t df. Okay, that is about a h of. So this one is about a frequency response function. And in another way, we can say that if we have this function, okay, we can say that impulse response we can rewrite with respect to that a frequency response function. So then we can have this function h of f and this h of t. Okay, so we have written here a h of t. We are replacing this h of f, h of f put here in terms of this one here h of t. So h of f can be replaced here. So we can get function h of t is equal to, okay, so we are getting the h of t is equal to whatever the gain here with respect to minus infinity to plus infinity here. Okay, that is about a complex conjugate of s of f exponential of minus j twice pi f t1 minus t df. Or we can write in another way also. So this s of the complex conjugate of f is equal to s of minus f. So we can rewrite again the h of t is equal to, that is a constant gain minus infinity to plus infinity. Okay, then minus s of f instead of that s of f here exponential of j twice pi f t1 minus t, that is about a df, or equal to, we can write a ga s of t1 minus, because our signal is what? S of t. So we are getting that a function h of t, this is about a h of t. Okay, so this one is about a h of t is equal to what? A ga, that's about a gain. So we are writing in terms of what? A signal again. Okay, s of t1 minus a t here. Okay, so this one just like we can say that we are representing the a function that is h of f in terms of what? A impulse response function, and that will provide you the a, a signal is of waveform. Generally, we can say that we have the signal waveform of a s of t. We'll write here for the signal of a s of t. This one is about a s of t here. So this is like a function. So this one is about a t1, and this one is about a received waveform and a impulse response function. We can say that a impulse response function. This one is about a t1 here. That is about a h of t. Okay, so there is a difference. Okay, so in terms of what a timing here, because impulse response of the match filter, we say that a h of t here, that will be the image of what a receiver form. But there is a difference in the particular the starting time of a frequency. So we can say here this one is about a replica one, but there is about a difference in terms of a starting time. So we can consider here the condition for this increasing the signal to noise ratio. We need to find out at what particular function is to be used, or we can say that rather we need to consider that the impulse response function. But sometimes that impulse response function we need to be right in terms of a s of t. Instead of that, we can write in terms of a s of minus t there, and that t, generally we say that t is to be less than 0, but we need to consider that t is to be less than t1, and then we can find out the conditions for the h of f with respect to for a given particular signal to noise ratio. So then what will be the filter characteristics here, okay, of a match filter? So generally we say that we have a h of f function, and that h of f function is a linear one as well as a time invariant, and that will improve. Okay, this match filter function h of f is nothing but what? A linear. Okay, this function is h of f, it will be a linear, and we can say that it will be of a time invariant filter, and that will be used to maximize the signal to noise ratio. Again, we have a complex conjugate of s of f and the exponential of a minus j twice by f t1. Okay, that is about a h. And we have considered earlier that noise is about a stationary one. Okay, noise, we say that it is about a stationary. When the noise is stationary, we say it is about a white noise. When we say that it is about a white noise, when we say that it is about a white noise, then what happen here? That is, a spectral density of this white noise will be a uniform. Okay, so you can say that uniform spectral density. Okay, uniform spectral density. So then we can consider that a ratio, a signal to noise ratio, that is to be maximized. So in that case, we need to find out the what will be the maximum value of a output signal voltage. Okay, so in that case, that ratio, signal to noise ratio, we can rewrite here for the what, for the signal to noise ratio we consider, and that is for the match filter function. In that case, it will be what, f0 of a t max, okay, that is where divided by a signal to noise ratio. So this one is about a signal to noise ratio, and this s0 of t, this one is about a maximum value of a output signal voltage. Okay, this one is about S0 is F0, that is FO output. Okay, and S of t, that is about the input signal. Okay, so we can say that S out. Okay, so this one. So that is about a maximum value, and that noise is nothing but what? A noise power at a receiver output. And this ratio we have defined here. That is again earlier we have defined the ratio that is same as a signal to noise ratio there. But only that a condition we consider here for this ratio to be defined, that will be a maximum value of a output voltage, just we are defined, because we are interested in what h of f will be this particular function that will use to increase the signal to noise ratio. It will maximize the a signal to noise ratio. So now we have defined here that r of f here, okay, that particular ratio, and that ratio is to be defined with respect to this h of f. Okay, that is about a filter function. So how to define this ratio in terms of a filter function? So then we need to consider a input signal value, and then we need to find out the output voltage of a filter response function h of f. So in that case, SO of t, okay, that is about the output in terms of what? A frequency response function. That is about what? The S of f, h of f, exponential of j twice pi f t, d of f. S of f is nothing but what? We have the input signal, and S of f is nothing but a Fourier transform of the input signal, means that is nothing but a received signal at a receiver. So we can define then a mean output noise power n is equal to what? A n out here, that is about the input noise power per unit bandwidth, by 2, and this 1 by 2 factor, because we have a limitations for minus infinity to infinity, and thus we are defining the n0, that is for a unit that per cycle here for the given particular bandwidth there. So that's why n0 by 2 here, and is equal to minus infinity to plus infinity h of f square into df. Okay, so this one is about a mod, both are a mod. So def we can substitute here in this rf. So we'll get this rf is equal to what? S0 by this one is about n0. So we'll rewrite here again by substituting equation. So we will get that a rf is equal to, by substituting infinity minus infinity to plus infinity, s of f h of f, okay, exponential of j twice pi f t1 df mod divided by n0 by 2 minus infinity to infinity here mod of h of f square by df. This is about a RF. So use a function Stewart's inequality. So in that case, we can say that Stewart inequality. Okay, so we say that it is about a continuous one inequality here. In that case, if we have a p and a q, both are a complex conjugate there, or a complex function, so we can say that a p complex conjugate of a p here that is about a dx. We say that is about integral is equal to q of complex conjugate of equality. So is equal to e will be greater than or equal to integral of p and q dx. That is about a maximum of this one. So we can use here a p complex conjugate is equal to s of f exponential of j twice by f t1 and q is equal to h of f. So if you put here in the equation of the r of f, okay, so in that case, that equation become what? This s of f will be separate out, h of f is to be separate out here, these two functions, and this one is about is separate. So we are getting that the r of f is equal to minus infinity to infinity mod of h of f bracket square df minus infinity to infinity. We have the mod of s of f bracket square df divided by n0 by 2 minus infinity to plus infinity h of f bracket square df is equal to, we can say that that is about a twice of it. So that's why we have a s of f here df by n0 by 2. This one is about a minus infinity to plus infinity. So this one is about a final equation. So that this one is defined in terms of what will be the energy required. That's why f of f is nothing but the energy. So